And there it is. Now, don't worry. Some of you are like, well, I put more effort into it and I didn't get a score which represents it. That's true. But don't worry. The people who just slopped through their homework, I'll get them tomorrow. And then justice will be served. It's called the test. Don't worry. No, there's a simple reason. Your grader was falling asleep in my other class, and I decided he needed a break. So there it is. But hopefully, he'll be rared up and ready to grade the next one. So anyway. Oh, so let's talk about mission 4. Here's a solution. Are there anything in particular that you want to know about in here? $47B. So 47 is a question about a ninja dog. So you got a ninja dog, Pakun, one of the many hounds of Kakashi. Speeds towards the base of a valley modeled by this lovely equation, where x, y, and z are meters. You're supposed to do what? I think first of all, I'm supposed to find the direction it decreases at the maximum rate. Right? So the gradient of z allows me to set up the directional derivative for z. And so the directional derivative of the function z will tell me the rate of change in z, right? So the maximum rate of change is when you go in the direction of the gradient. The minimum rate of change is when you go opposite the direction of the gradient, right? So it stands to reason if the gradient of z is 9 comma minus 5, then minus that direction gives you the rate in which you're going down the hill the fastest. Taking z as being the upward direction, obviously. So then what? Part B, I gave you that the x velocity was 3, the y velocity was 4. It said find the speed at 1 comma minus 1, 7. Well, this is a three-dimensional motion, so the speed should be the square root of the x velocity squared plus the y velocity squared plus the z velocity squared. In other words, it's the magnitude of the vector velocity, right? So I differentiate implicitly, and that's the relation, right? So I just differentiated the equation, and that's what I had. So what was the original thing was what? How do I differentiate? So just to be clear, up here, I had z is equal to 5x squared plus xy plus 3xy squared, right? So if x, y, and z are functions of time, differentiating that with respect to time gives me dz dt is equal to 10x dx dt. And then I have to do a product rule on the xy term, right? So I get dx dt times y plus x times dy dt, and then plus 6y dy dt, just differentiating implicitly. Any questions? I mean, you see where this come from? Yep.
Would the negative of the answer for A also be correct?
No.
I assume it would not. Okay.
No, because we're looking for the direction in which it's decreasing. So the without the minus, that would be the direction in which z is increasing the fastest. That'd be going up the hill. This is going down the hill as fast as you can. Does that? So the speed, again, is the square root of dx dt squared plus dy dz squared plus dz dt squared, which ends up being the square root of 74 meters per second, or about 8.602 meters per second. Does that make sense, or no? Okay. Yes?
Can you go over some questions
From test 2? You mean from last year? Yeah, we can do that. But before I do that, are there any other questions about this one? Yeah.
Yeah, I think it's 51 part B. I know I got it wrong because I didn't remember when you could multiply both sides. Yeah, you need to make it exact. Can you always make it exact?
Well, that's the, so no, I mean, No one yet. Yes and no. All right. Here's a similar issue. Can you always integrate a continuous function? So I tell you integrate from 0 to 1 sine of x squared dx. Sine of x squared is continuous. Can you integrate it? No, you can't, because you can't find an antiderivative of sine of x squared. Right? Well, I mean, you can in a power series sense, but pragmatically you can't. So that's kind of a similar issue here. There's something called Pfaff's theorem, which says that there is some function I can multiply on that equation and make it exact, but the problem of figuring out what the integrating factor is it's as hard as solving the problem. So it's kind of, you know, you have to be kind of given, hey, here's a template for the integrating factor, and then you can work out what that has to be on the basis that the equation becomes exact. What was this one here? But here, I guess this one just wasn't exact, so that was the point, right? Oh, so I either need to make it exact, or this one actually is kind of an oddball question. I think my next thought is that I wouldn't do that. Instead, I would just solve it by separation of variables, like in Calc 2. And so doing that, I see now that, so at that point I realized, oh, there's a typo in this problem. Now, fortunately, the grading of this was very generous, so otherwise, even if the grading wasn't generous, I would have had to tell the grader to drop this problem because there was a typo. I wanted it, what I intended to write there was this. This was the intended problem to put there. And if that was the case, then this would have been the function for which it's the level curves are of that function are the solutions to that exact equation. So I was trying to make a connection with a previous problem in this homework, and I made a typo in writing this one. The previous problem I'm talking about was maybe part A. Yeah, see, because part A, we had 1 plus e to the y, x e to the y plus y squared, right? I wanted to put those same things. Oh, I'll see if I can get it on the screen. See, I wanted for the x component of A to match this, and I wanted the y component to match that, so you could see it's the same problem. But somewhere in the production of this problem, I got distracted and made a mistake. So this got put there instead of the x e to the y plus y squared, which is what I meant to put there. And I did an example in class like that before the break to try to make this connection between finding a potential for a vector field and solving the exact equation. This was supposed to be that. But any other questions about the mission 4 solution? Yes, sir. 50 what? Sure. So here's 58. And basically the idea of 58 is to change coordinates. You want to use the chain rule. So if I want to change from derivatives of x to derivatives of u and v, what I do is I just do partial x is partial x, partial u, partial u, plus partial v, partial x, partial v. Now, you could write this rule having a function being operated on, right? Or you could just write it like this with the understanding that this is an equation which is true for all functions of an appropriate domain. And so if I do that, you see I can differentiate the u formula and the v formula, and see where do you see where the 3 and the 1 comes from here? It's like partial v partial x is 1, partial u partial x is what? 3, right? And I do the same for the y derivative. And then these are really easy because there's no functions here. If there are functions here, I actually have to think about product rules when I do the next step. But since these are constant coefficients, they basically just multiply like polynomials. And you get this, and you get that, and you just add them, and you get this horrible equation. So this is Laplace's equation in the uv coordinates. It's 13 second u derivative plus 10 the mixed derivative plus twice the v derivative, the double v derivative. If you want a harder version of this, try to do the same thing, but converting from polars from Cartesian to polar coordinates. That I have the answer for in the notes, and I have a start of the calculation, but I didn't quite do the middle of it, and it's one of the examples in the notes. It's like this, but anyway. Other questions? 60, yeah. So 60, The basic idea here is that the possibility or the impossibility of the differential equation being exact basically boils down to these second derivatives commuting. So those are the conditions you actually need to be wary of. And so if you look at that, if I've got 4 variables, it turns out they're what? There's like the first with the second, the first with the third, the first with the fourth, the second with the third, the second with the fourth, and the third with the fourth. Count them 6 different consistency. And so when you trace out through that, you'll get 6 conditions. Now I have derived those in the solution by a sneaky way. I used this exterior derivative I showed you guys about, but it's just, I'm just having fun. You obviously don't need to do it that way. In fact, the equation which is boxed with a star around it, you can just think about that directly and trace through the different possibilities. Eventually, you'll get to the same thing I calculate down here as I calculate the derivative, the exterior derivative of the differential form. I get these 6 different 2 forms, xy, zx, tx, yz, ty, tz, and the coefficients, these being 0, are precisely the conditions that we need for exactness. But my calculation gives me a way to see it without just enumerating possibilities. I can just do a calculation. This is not required material, obviously. But once you see through it, this is the one we had from n equals 2. Qx equal to py was what we said. If a differential form p dx plus q dy has this condition, it's said to be a closed form, right? A little bit, not too much later in this course, about 3-4 weeks, I forget exactly, we'll find that we need these 3 conditions for the 3-dimensional vector field to be conservative. Qx equal to py, we know that one. For a PQ, if the vector field is PQR, we need this, this, and this for the vector field PQR to be conservative. And then for 4 dimensions, there's an extra other 3, which are, I don't know what they mean in terms of 3-dimensional geometry, but anyway, that was the answer. Which is really just a extension of what we did for 2 dimensions to more derivatives mixing. We still haven't proved that if those conditions are met, that implies that it's exact. All we know right now is that if it's exact, those conditions have to hold. So the converse to that requires a theorem we don't yet know, which is called Green's theorem, or later Stokes' theorem. So, okay, so let me get over to Christina. You wanted me to look at test 2, right? It's probably a good idea. Hey. Actually, where are we? Bless you. Do you want me to put a TNB problem on test 2 just for like nostalgia's sake? No? Okay, just checking. I'm just messing with you guys. I wouldn't do that. Let's see here. Where did I put test 2? Somewhere down here. Where did my cursor go? Oh, there it is. All right, so problem 1. If I ask a question like problem 1 on your test tomorrow and you don't get it, I kill you. Right? This is a gift. I'm trying to freely give to you. But as we know, people don't always take freely given gifts, right? It's a problem with us humans. Sometimes we're stubborn. Any questions about this? I don't think so. But you do need to know this cold, right? If I give you a function of 2 variables and I say find the tangent plane at a point, you should know what you got to do. What do you got to do? Take f of the function plus fx at the point, right? I mean, this is f of ab plus fx ab times x minus a plus fy of ab times y minus b, right? So you just plug in the point 1, 2. So if I plug in 1, 2 into fx, I get what? I get 1 plus 2 times 4, I get 9. That's this 9. If I plug in 1 comma 2 into here, I get 1 times 2, I get 4. That's this 4. What's this 5? 5 is f of 1, 2, which is what? 1 plus 4, which is 5. Do you guys see it? So that, of course, is the fundamental significance of partial derivatives, is they give you a way to linearize functions of several variables. Now, is there a particular question you had? Is there something?
For 14, I just didn't know how to use different forms of
Yes. So here we have a differential form, minus y dx plus x dy is this form closed. What does it mean? What's the definition of a closed form? See, if you don't know that, you can't answer it, right? What's the definition of a closed form? So we have p dx plus q dy is closed if and only if qx is equal to py. So, in other words, the condition I keep telling you guys about is that exact implies closed. That was, if the differential form is exact, that has to imply closed. That was, this implication comes from the second partial derivatives commuting for the level function. So that's what I'm doing here. I'm checking the y derivative of the x component. The x component is minus y, right? P is equal to minus y here, right? Q is equal to what? X. So partial y of minus y is equal to minus 1. Partial x of x is equal to 1. Minus 1 is not equal to 1. So it's not closed. So that implies it's not exact. Yes, sir.
For number 3,
Mm-hmm. Yeah, sure.
after you take the gradient at a point, how do you determine the direction?
After you take the gradient at a point, how do you determine the direction of what?
In which f is locally constant.
F is locally constant. Well, we know the gradient points in the direction in which it's increasing, right? And we also know that the gradient dot with a vector gives us the directional derivative, right? So think about this. The directional derivative in the u-hat direction of f at the point P is equal to the gradient of f at P dot u, right? So if it's going to be at the point P, if you want the direction in which it's, suppose this is the direction of the gradient. You want the direction along which it's locally constant. It's what? It's where it's perpendicular, right? This is going to be 0, the directional derivative will be 0 if u hat is perpendicular to the gradient. So you want to rotate by 90 degrees from the gradient direction, whatever that is. And so this will be the direction it's locally constant along that line. And of course you can see that, right? Here are some level curves of the function. And if you look at it, the gradient vector field points radially outward, right? Like that. There's an integral curve of the gradient vector field. And as you can see, at that point, that's the direction along which it's constant, right? And of course, these circles are the level curves. So there's always this sort of duality between the direction in which the function's increasing and the direction in which it's staying constant. They should be perpendicular to one another. Assuming the gradient's not 0. If the gradient's 0, all bets are off. The geometry that I'm talking about breaks down there, because everything is perpendicular to the 0 vector. Yeah.
In this problem, any pair of numbers would work for the vector as long as they were equal in magnitude but opposite in direction.
No, I don't. I gotta.
1, -1, square root of 2.
The direction in which. Yeah, I would have, in the 1 - 1 direction, I would have also taken the -1 1 direction I would take the 2 minus 2 direction. I mean, if I don't want to grade so many different possible answers, I might say, give me a unit vector. Then there'd just be 2 answers to grade, right? Plus or minus this divided by the square root of 2 would be the directions in which f was locally constant at that given point. So number 2 here looks like just a straight directional derivative question, right? So there I'm just seeing, can you differentiate, and do you understand what the directional, I hope you guys understand the connection between the directional derivative and the gradient vector, right? They're not the same thing, but they're related, right? To construct the directional derivative at a point, we calculate the gradient, plug in the point, and then we take the dot product with the direction in which we're interested in the change. Now, there's one important caveat to that. This does indeed have to be a unit vector, right? So be careful if you're calculating directional derivative that you're taking the dot product with a unit vector, right? That's part of the deal here. So if I give you a vector like 8, 6, don't be fooled. That's not a unit vector, right? 8 minus 6 is a vector of length 10. So I have to divide by 10 to make it a unit vector. Yeah, that's right. So I usually take off like 2 points for not making it a unit vector, but they're 2 points that you'd like to keep, right? So it won't make you fail the test, but it will make you regret your life to miss these points. Because you'd like to miss these points on something more like meaningful, right? No, I mean, don't miss the points at all. How about that? That'd be better, yes. Let's see here, what do we got? I think I forgot to put on the instructions here, and I will try my best when I write your test tonight, probably. I mean, I guess it better be tonight if it's not already written. Did I write it? I don't think I wrote it. I don't know. Anyway, it doesn't really matter. I wrote the answer here in terms of x and y and z. Those are intermediate variables, right? So unless I say otherwise, let it just be understood that you can give your answer in terms of intermediate variables. You don't have to plug in. Like technically, I could plug in y is beta squared sine beta and, oh. Whoa. Are we done? I'm not talking about sneezing. I'm talking about the gosh. I can't look at that. Oh. Do you guys know what I'm saying? No. You may leave your answer in terms of x, y, z. You don't have to put everything in terms of alpha and beta. X, y, and z are intermediate variables for this problem. Oh, I'm sorry. X and y are intermediate variables for this problem, right? Z is the dependent variable. X and y are the intermediate variables. Alpha and beta are the independent variables. If I was to tell you, leave your answer in terms of the independent variables, then I would only want to see alpha and beta in the answer. And that would be horrible for me to grade, for you to write.
It would dramatically increase the chances of someone somewhere making an error.
Yes. I would definitely get more points if I did that. But I told you guys before, I have enough points. I don't need any more. Yes?
Is there going to be any linearization problems on the test?
Yes. Thanks for reminding me. In fact, there already was one.
Well, we saw that, and that's why we were wondering if it was going to be on the test.
No, but I sometimes ask the following question. I say, calculate the x derivative, calculate the y derivative. Find the equation of the tangent plane. And then next part, find the linearization of the function at the point. And I have people leave it blank, which is sad to me because they should know that the tangent plane is the graph of the linearization. So the linearization, like this right here, is not the linearization, right? This is not the linearization. This is an equation, right? This is the equation of the tangent plane. So, but if I peel off the z, right, and I just write L of xy equals to this stuff, that in fact is the formula for the linearization. So, I mean, if you can find a tangent plane, you can find the linearization. I mean, at this point, you should ask the question, why do people get this wrong? I do not know, but they do. Did I do another one somewhere?
I ran a quiz elsewhere. I thought I saw something,
I mean, I usually ask that question somewhere.
but I'm also confused. So
Yeah. I wish I had more idiots in my class. Let's see here. Sorry, that's sort of a backhanded compliment, I think, on that. Yeah. You'll take it. So here's a token, hey, you have to use the chain rule to solve this because you didn't get formulas question that I warned about, right? The only way you can solve this is to symbolically use the chain rule because you don't actually have a formula for h, right? So you're forced to think symbolically. Partial g, partial u is partial h, partial x, partial u, plus partial h, partial y, partial u, because g is equal to h of x, comma y of u and v. So that's just the, it's sorting through the chain rule. Everyone clear on how to find the normal vector field? What are the two ways, usually two ways we have to find the normal vector field? If you're given a level function, if you're given a level surface, right? If you're given f of x, y, z equal to a constant, how should you find the normal vector field? You take the gradient. It's a three-dimensional vector field, right? Done. That's it. Easy. If you have your surface, if it's parametrized, right? In other words, you've got something like this. R of s comma t is equal to formulas. I think this happens to be a helicoid, whatever. Then to calculate the normal vector field is a little bit more trouble. You calculate the partial velocity in the one coordinate, partial velocity in the other coordinate direction. And then you take the cross product of these things, and that's the normal vector field. We also have some special formula for a graph, which I would encourage you to put on your note card in case it came up. But what can you always do? You can always take a graph, and you can always either convert it to a level curve, to a level surface, right? Or you can take a graph and convert it to a parameterization, depending on what suits your purposes. I think if you're asked to find the normal vector field to a graph, the easiest thing, I think, if I was faced with that problem, I personally would say, I take your z equals to f of x comma y, and I will trade it for this. Because this is just so much easier. If I want to calculate the normal vector field to that, that's easy, right? If I choose instead to take this and look at it as a parameterized thing, which is also not hard, right? There's the parameterization, which gives you back the graph using x and y as parameters. You could do that too, right? But then you got to take the cross product of the partial velocities. And cross products, they're a drag. So we try to avoid them if we can, right? I don't know. If I had freedom, the responsible thing to do is to use the level surface idea if I can. Any questions about that? You guys are still on break, huh? All right. How do you find the normal line? What's a normal line? It's a line that points in the normal direction, right? So to find the normal line to that surface, I just calculate the normal vector field, which is given to me by the gradient, and use that as the direction vector for a line. Right? And then this problem has a little bit more to it. I tell you it has direction vector 12, 12, 12, right? So I got to find x, y, and z such that I get 12, 12, 12 from this, and it forces me after I plug it in to put a equal to 6, b equal to 4, and c equal to 3 apparently. So the most important thing, from this question really is this idea that the normal line should line up with the normal vector field, right? That's what we mean by normal line. And past there, it's just stuff we already know applied to this problem. I hope that's the case. Oh, limits. Hey, limits. Let's not forget about limits. Any good Calculus 3 instructor will want you to learn two things probably in the limit sections. The one is that you can change to polar coordinates in order to do certain two-dimensional limits in a nice way, right? Sometimes you can actually calculate them, these specific values, by making a polar change of coordinates. The other thing, probably the most important thing, is this idea that if the limit doesn't exist, you should think about trying to find two different paths that you can approach the point, and if you get different values along the different paths, then the limit doesn't exist, right? The so-called two-paths disagree implies does not exist. I don't know, there's no good name for this thing. But the point is, if I can calculate two path limits and they don't agree, the multivariate limit can't exist. There's also a one-path test too, right? If you can find one path to the limit and that path doesn't exist, that's also that's you can give up there. See, because if the multivariate limit exists, that means that all the path limits have to exist and be equal. So if even one path fails to give you an existent limit, you're done. So that every so often comes up.
So you said two-path thing and what else?
If you get two paths which both give you something that exists, like one goes to 1, but the other one goes to 2, well, 1 doesn't equal 2, so the multivariate limit doesn't exist.
That part, but so there's two things we need to know about limits. And then I got
The other is changing to polar coordinates is sometimes helpful. Sometimes changing to polar coordinates will show you how to make the two-step path. Like here's one. Limit as xy goes to 0, 0 of x squared y over x to the 4th plus y cubed. So if I change to polar coordinates, I get what? Limit r goes to 0. I just basically put x equal to r cosine theta. I put y equal to r sine theta. So it's going to be like an r cubed cosine squared theta, sine theta. Let me make this easier. Let me make this x squared plus y squared there. That's easier. So this gives me r squared downstairs, right? And so what you're left with, limit as r goes to 0 of r cosine theta sine theta. Now, this cosine theta sine theta, if it was sitting there by itself without that r, it would be very troublesome, because different values of theta, right, which are different rays going into 0, would give you different values, right? But who cares, because you've got something which is at most plus or minus 1, right, multiplied by something that's going to 0. So you've got something that's going to 0 times a bounded term, it goes to 0. So there's that's an example of the first thing I was talking about. The third thing, which you guys love, is the squeeze theorem. Right? The fourth thing, which you guys actually love, not sarcastically, is when the limit is just stupid and you can just plug in the point, right? Like if I have f of x, y is equal to x squared plus y cubed plus the sine of xy going to some point. Well, it doesn't matter what point it is. You can just plug in the point and the formula makes sense, so done. Those are the other kind, but I don't know. I don't usually ask about those because you guys know how to do them, so there's no fun in that. Oh, I'm sorry, I must just tell you that, yeah.
How did you know that the sine over r grew up?
R goes to 0. Sine is between plus or minus 1. Hmm? Oh, so there's an example of the one path does not exist, makes everything die. I mean, this is the one path does not exist test. I have no good name for it, but the point is this multivariate limit, xy goes to 0, 0, is dead to us after we learned that this single limit, the limit along the what axis is that? That's x equals to 0. That's the y-axis limit, right? the y-axis path blows up to plus or minus infinity, depending if you look from the positive or the negative y-axis. So that one approach to 0, 0, giving you infinity or minus infinity, is enough to kill the whole thing. Because if the limit exists, all possible different directions have to give you the same thing. Yep.
Why do you have only r going to 0 and r infinity?
Well, geometric. I mean, like, think about it geometrically. Theta doesn't go to 0 as you approach the origin, right? Theta goes from 0 to 2 pi. So
You have x and y, which is defined in terms of.
I mean, just think geometrically what it means for x, y to go to 0, 0. It means you're approaching the origin, right? So if you actually get to the origin, theta's not even defined. So there admittedly is a bit of analysis here that we never really flesh out in here, but it's actually reasonable. So
That makes sense.
yeah. Hey, this is that Pekun question again, isn't it? You're stuck on this surface. I give you an x velocity. I give you a y velocity. Find the z velocity. Right? Now, this isn't a question about speed, so I just asked you to find dz dt, so you don't have to do the square root of sums of the squares, right? Because it's not about the speed, it's about the dz dt, the z component of the velocity. But this is essentially that first question on mission 4, right? It's the same question, just twisted a bit. Yes, sir. Or ma'am, sorry.
What are the dots? What is that supposed to be?
Oh, that's a time derivative. X dot is equal to dx dt. It's a standard, non-standard notation.
What does that mean?
I mean, it's standard too. It's standard. Well, I didn't make it up. I mean, this is kind of old. I mean, you got to blame Newton. This is ancient notation. Yes, we can move on. Imagine yourself a pig. Ron Swanson is holding a barbecue of epic size. What?
How is your mentality thinking of this problem?
I think I must have been watching Parks and Rec at the time. I must have. Yeah, we can do 12. So the point of problem 10 is that the gradient of the smell function gives you the direction in which the smell is increasing. All right?
But why do we want to get away from the bees?
You're a pig.
Imagine yourself.
Imagine yourself a pig.
I thought we're imagining a pig.
No, you're like
Oh, so I'm a pig.
you're a pig,
Oh, I
right?
get that.
And if you know anything about Ron Swanson, you'd know that he would butcher you there. Like, you're like, well, I'm a pig. There's no butcher shop, so it does no problem. But he'll butcher you. The total differential, right, for a function of several variables is just partial f, partial the first variable, d the first variable, plus partial.
I was wondering where you got f equals that from. Like, how you got that.
Oh, guessing. Oh, no, that. Oh. Properties of logarithm. So yeah. So the natural log of ABC, well, AB is natural log A plus natural log B, right? The natural log of e to the c is c ln of e, but c ln of e is just 1, so it's c. So so what I'm using here are properties of logarithm, which it may be a little rusty, but in Calculus 1 we use these for logarithmic differentiation with great effect. So natural log of e to the x gives me x, and then I have plus the natural log of z to the z squared. So the power law for the natural log brings down the z squared, z squared natural log of z for that. This piece simplifies to 1 because we know the hyperbolic identity, cos squared minus sin squared is 1. And then there's a half from the square root, and then the natural log, secant 1 over cosine, so the natural log of 1 over something is minus the natural log of the something, which brings out the minus because secant 1 over cosine, and then y squared. And so I would rather differentiate this is the point. This isn't actually a Calculus 3 question. This is just a punishing students for not knowing pre-calculus question, just to remind you there are things you're supposed to know. I mean, Yeah, but I think I'd done stuff like this that semester too, before this test. Of course, now that you've asked me about this question, I've also done stuff like that this semester. Thank you. No, but do you see them? Silly comments aside, do you see what I did? I mean, there's the moral of this problem is basically think before you differentiate. If you can make an algebraic simplification to your expression, it's worth doing that sometimes before we differentiate. That's even more true if you're taking multiple derivatives, right? If you can regroup things in a way that makes the differentiation more efficient, it's often worth it. Hey, problem 13 is just a standard exact equation, right? I hope you guys can do those by now. I've spent a fair amount. I think I spent more time this year than I have in the past on actually showing you how to do these. So, like, to solve this, I can hope that it's exact. If I do, this should be the x derivative. This should be the y derivative of some function f. And you can see that this works, right? X squared y squared plus e to the x. If you differentiate with respect to x, I get that. If I differentiate with respect to y, I get that. Which then shows me that the big F equal to a constant is in fact the solution of the given equation. So here I'm actually going through the process. You know, I integrated this one, and then I plugged it in to the second one. That gave me the derivative of C1 with respect to y is y cosine y squared, and then I do a u substitution to integrate this, which gave me finally this answer, rather. So anyway, I hope you, yeah, go ahead.
If we just differentiate both of them and compare to see if they're the same, is that acceptable?
Yeah, I'm interested in the answer here, not the process so much. That said, you may be in a class after mine where it's expected you do it this way. Because the compare and take the common terms method breaks down when it's not actually possible to do it. If you try to find a function that's the differential, I mean, if you try, for example, getting back to the vector field problem, if I have a vector field p comma q equal to the gradient of f, and I just integrate the p term and I integrate the q term with respect to x and with respect to y separately, and then like take the common terms and say that's the little f whose gradient gives me back the vector field p comma q. I mean, you can do that, right? But it could be that your answer is nonsense. Now, there's a simple way to guard against that is you check your answer. You take the gradient of what you say is the level, as the potential, and if you actually get back the p comma q, you're good. And if you understand what I just told you and you can argue to the next professor who doesn't want you to do it that way forcefully that you're still right, then maybe you can still get away with it. I don't know. Yes. But that professor may just like his logic, and that might be that you have to do it this way. Logic is logic. Well, I mean, there's logic and there's logic and there's law. You should not conflate the two.
I don't like when presidents make their own laws.
You don't like when presidents make their own law, then you should leave America. That's un-American, what you just said. I mean, the president's a dictator. He should be able to say what he wants. It's the American way. It's a benevolent. This is a benevolent dictatorship.